Hello again, and welcome to our second of two lectures on conic sections. Last time we looked at circles and parabolas, and you might remember that we actually defined them as a locus of points satisfying a certain property, a set of points satisfying a certain property. Well, that'll be the key to today's lecture when we'll talk about ellipses and hyperbolas. And I'll be honest, I'm going to spend more time on ellipses than hyperbolas because I like them a lot better. They're more interesting to me. Both are important, but without a doubt, ellipses are more important. Again, there are a lot of applications of these conic sections. Ellipses occur, for example, modeling planetary motion. And we'll also see later on in the lecture some whispering gallery application, a whispering gallery application. Let me also add that if you go on and take a calculus course, you'll use conic sections. You'll be graphing parabolas and ellipses and things. But if you go on to third semester calculus, you keep going in calculus, all these figures will suddenly become three-dimensional. You might remember last lecture we took a parabola and rotated it to create a paraboloid. This can be done with circles, they become spheres, or it can be done with ellipses. And when you rotate an ellipse, it kind of looks like a football. All right, so let's get going. What's an ellipse? What's the technical definition of an ellipse? Well, it's a set of all points x, y in the plane, the sum of whose distances from two fixed points is a constant. And these fixed points are called the foci, the plural of focus. So there's one focus here and one focus here, and the set of all points equidistant from those two foci is the ellipse. And here's a picture where the point xy is equidistant from the distance from focus 1 and focus 2. In other words, d1 plus d2 is always a constant. And the shape is that oval. Okay, now there's some terminology associated with this. The line through the foci intersects the ellipse at 2 points called vertices. And the chord joining the vertices is the major axis, and its midpoint is the center of the ellipse. And then finally, the chord perpendicular to that major axis is the minor axis. Here's a picture with all those characters labeled. There's the center of the ellipse. There are the two vertices, and that's the major axis, the longer axis. And then you'll see the chord joining that forms the minor axis, perpendicular to the major axis. Okay, given that definition as a locus of points satisfying a certain property, you can develop the equations of ellipses. And it's a little complicated. Let me show you how it works. Assume the center of the ellipse is hk, and assume the major axis is length 2a. So it's a from the vertex to the center, and another a from the center to the other vertex. So the major axis is 2a. The minor axis we'll call 2b, so A is bigger than B. If the axis is horizontal, so the ellipse is kind of elongated horizontally, the equation is x minus h quantity squared over a squared plus y minus b quantity squared, y minus k quantity squared over b squared equals 1. And if the ellipse is sort of vertically shaped, it would be a reversal, x minus h quantity squared over b squared plus y minus k quantity squared over a squared equals 1. Here are pictures of those two situations. In this picture, you see the center hk, you see the major axis of length 2a, the minor axis of length 2b, and that's the equation x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. The second case, you see the ellipse is kind of vertical looking now. The center is still hk, but now the major axis is 2a, is a vertical axis, and the minor axis is 2b. Okay, there's good news if the center is at the origin. Everything simplifies beautifully, and you get the equations x squared over a squared plus y squared over b squared equals 1 if it's a horizontal major axis, and conversely, x squared over b squared plus y squared over a squared equals 1 if it's a vertical major axis. Those are kind of the equations that are kind of more fun to work with. They're a lot simpler, of course. Now remember those foci that sort of gave rise to this definition of ellipse. Where are they located? Well, there's an equation relating the foci with A and B. And the equation is that the foci lie on the major axis, that's for sure, and they're C units from the center, where C squared equals A squared minus B squared. Remember that A was bigger than B. A is the major axis, 2A is the major, 2B is the minor. So C squared, that's a positive number, thank goodness. It's A squared minus B squared. All right, that was a lot of terminology, a lot of A, B's, and C's and things. Let's do an example and kind of put it all into place. And fortunately, you'll have some other examples to practice in the workbook. So let's sketch the ellipse 4x squared plus y squared equals 36. Let's analyze this ellipse. 4x squared plus y squared equals 36. And before we start, notice something kind of curious. Suppose that 4 were not there. What would you have? You'd have x squared plus y squared equals 36. Who's that? What's that? Right, that's just a simple old circle, isn't it? Well, with that 4 in front, it's no longer a circle, but it kind of looks like a circle. It's a distorted circle. It's an ellipse. Let's analyze it. Let's find all the pieces in those formulas. All right. I suggest doing the following. Remember, in the formulas, it's something equals 1. 1's on the right-hand side, and our right-hand side is 36. So let's divide by 36 and get rid of it. So divide both sides by 36, we get 4x squared over 36 plus y squared over 36 equals 36 over 36, which also goes by the name 1. So now we have x squared over 9, 4 and the 36 simplify, plus y squared over 36 equals 1. That's very close to the standard form. The only difference is, remember, in the denominators, they were a squared and b squared. So write 9 as 3 squared and write 36 as 6 squared. Now that's the standard form. That's it. X squared over 3 squared plus y squared over 6 squared equals 1. So who are our characters here? What's A and what's B? Well, A is the larger. So A is 6 and B is 3. Okay, good. Where's the center of this ellipse? Thank goodness, it's at the origin. So the center's at 0, 0. And A is 6 and B is 3. So it's a vertical major axis, isn't it? Because the larger number, 6, is below the y term. Okay, so the vertices then are 6 units away from the center. So they'll be at 0, 6 and 0, minus 6. Good. Okay. How about the foci? Where are they? Well, remember that equation, c squared equals a squared minus b squared. And we know a and b. So plug it in. 36 minus 9 equals 27. So c's the square root of 27, or if you simplify, it's 3 root 3. And on a calculator, that's about 5.2. So now we know a lot of things about this picture. We know where the vertices are, where the center is, and we know where the foci are. They're 3 root 3 away from the center. So you could plot those 2 points, 0, 3 root 3 going upwards, and 0, minus 3 root 3 going downwards. Here's a picture of our ellipse that we were savoring there for a while. There's the center at the origin, 0, 6, and 0, minus 6. Those are the vertices. It's a vertical major axis. The foci are indicated, and notice something. It's kind of cool. The foci are very close to the vertices, aren't they? They're really close. And we'll talk about that in a moment, but keep that in mind, how close they are to the vertices. And then it turns out, remember, B was 3, and that's the minor axis, and you see that it intersects at minus 3, 0 and at 3, 0. So there's, a nice-looking ellipse, an elongated circle. All right, your turn to be the teacher. A student comes running up to you after you start talking about ellipses and said, "Professor, weren't we just talking about that? Didn't we talk about circles? What's the relationship between circles and ellipses? How are they What's the interplay there? How would you answer that? Well, here's how I like to think of it. I like to think of circles as kind of a special case of ellipses. If those foci are close together, the ellipse starts to look more and more like a circle. And in fact, if you could imagine the foci becoming one single focus, that would be the center of the corresponding circle. And in fact, this is such a good question that we can explore it more. There's a concept called eccentricity, which describes the ovalness, how round an ellipse is. So let me talk about eccentricity for a moment. It's kind of interesting how this works. The bottom line is some ellipses are very, very round. They almost look like circles. And others are kind of long and skinny, like the previous example. And what did you notice in that previous example? Remember how the foci were very close to the vertices. So keep that in mind when I define eccentricity. It's defined to be C over A. Remember, C and A are parts of our formulas for ellipses. C over A is the eccentricity, and it's the measure of the ovalness. Now let me analyze this new number. And this is not the E of the base of the natural logarithms. This is a different E. It's the quotient C over A. Okay. Notice, first of all, that A is always bigger than C. So this number is between 0 and 1. Now, what if this number is really close to 0? That means that C is very close to 0. What does that mean? That means that if C is close to 0, the distance from the focus to the center is very small, and your ellipse is very circular. It almost looks like a circle. Here's a picture of an ellipse having foci very close to the center. C is very small. On the other hand, if the eccentricity is near 1, that would mean that the quotient C over A is near 1, so C is approximately equal to 1, like in the example we did a few minutes ago. And in that case, your ellipse is quite elongated. Here's a picture of an elongated ellipse. And notice now the foci are far away from the center. They're getting close to the vertices. So this eccentricity measures, again, the ovalness, the roundness. And I told you that, or I mentioned that the planets move in elliptical orbits around the sun. And in fact, the sun is one focus of that orbit. And the planets hence have an eccentricity. Some of them move in a very circular kind of orbit, and some are a little more oval. It turns out that Mercury has the greatest eccentricity of all the planets, and it's about 0.2 or a fifth. All the other planets have eccentricity less than 0.1. Their orbits are much rounder, much more like a circular orbit. Kind of interesting, I thought. Okay, let's move on now to these whispering galleries. I find this really kind of interesting. In Washington, D.C., in the United States Capitol building, there's a room called Statuary Hall, and it's an elliptical room. It's shaped like an ellipse. You can imagine an ellipse around me, and it's called a whispering gallery for the following reason. And I've been there. It's really neat how this works. It's shaped like an ellipse, so it has two foci. And it turns out if you stand at one of the foci and your friend is standing at the other one, and you talk, then even if you're whispering, which I won't do, but if you whisper, all the sound waves bounce off the walls of Statuary Hall and go over to the other focus. There's that reflective property, similar to that reflective property of parabolas. So if you're standing at the focus and you whisper, your friend can hear what you're saying. And it's kind of cool because if your friend then moves slightly off the focus, he or she won't hear a thing. You have to be at the focus, and you can hear everything. And I've been told stories that political secrets were uncovered because people didn't realize they were standing at one of the foci, and the other people were listening at the other one. Who knows? Yeah. So let's play with this statuary hall a minute and talk about its shape as an ellipse. It turns out the dimensions are, it's 97 feet long and it's 46 feet wide. So we can actually figure out the equation of this whispering gallery. And we can also find where the foci are. So if you go visit, you can stand on them yourself. Let's figure out the equation. All right. The larger distance is 97 from vertex to vertex. So A is half of that, 97 over 2. And then the minor axis would be 46 over 2, or 23. That would be the B value. So now we know A and B. We can write down the equation of the ellipse, assuming that the center is at the origin. And we have x squared over a squared plus y squared over b squared equals 1. And plug in the numbers, x squared over the quantity, 97 over 2 squared, plus y squared over 23 squared equals 1. And that's your equation of statuary hall, with the center at the origin. Now, where are the foci? Well, remember, a squared minus b squared. And so plug in the numbers, 97 over 2 squared minus 23 squared, all square rooted. Plug it into your calculator, you get about 42.7. So the distance, the foci are 42.7 feet from the center, and the distance between the two foci would be double that, or about 85.4 feet. Notice that the C value, 42.7, is pretty close to the A value. This is a fairly elongated room. Okay, on we go to the other, or the final conic section that we'll talk about, the hyperbola. The equations will be very similar to those of the ellipse, with a slight twist, and I find hyperbolas a little more complicated, so we won't dwell on them as much as we've looked at ellipses. But I think it's important to realize where they come from and what their general shape is, so that if you go on and take a calculus class and suddenly a hyperbola appears, you'll at least say, oh yeah, I remember the general shape of a hyperbola, etc. Okay, so we'll start off the same way we did the other ones. We'll define it as a locus of points satisfying a certain property. And the property is very similar to that of the ellipse with a twist. Here it goes. A hyperbola is the set of points x, y in the plane, but now it's the difference of whose distances from two distinct fixed points, called the foci, is a positive constant. Here's a picture of what I'm talking about. You have two foci, a focus here and a focus here, and a point xy is on the hyperbola if the difference of the distances is constant. d2 minus d1 is a constant. Okay? It's kind of complicated. It's not the sum of the distances anymore like it was with an ellipse, but now it's the difference. And it turns out with this definition that the difference is a constant, you can derive the equations of a hyperbola. And it has two pieces. It has two branches, as indicated there in the figure. Now, there are some terms that go along with this definition. Again, it has those two branches. The line through the foci intersects the hyperbola in vertices. Okay, so there are two vertices where that line intersects the foci. And then the center is the midpoint between the two vertices, or between the two foci. That's the center of the hyperbola. The line joining that line is called the transverse axis. And again, the midpoint of that transverse axis is the center. There's some distances here that are kind of staring us, and these will play the roles of those letters A, B, and C that we had with ellipses. A is the distance from the center to the vertex, and C is the distance from the center to a focus. Okay? So A is center to vertex, C is center to focus. Okay. Now, given all that, and it's quite complicated, you can derive the general equations, the standard equations of hyperbolas. And let me show you the one when the transverse axis is horizontal. So the hyperbola goes like this, and the other branch is over here like this. All right, its equation is as follows. X minus h quantity squared over a squared minus y minus k quantity squared over b squared equals 1. Kind of looks like the ellipse equation, doesn't it? Except now it's minus in the middle there, not a plus. The center here, we're assuming, as usual, is h comma k. And of course, we'll get great simplifications if h and k are both 0, if we're at the origin. That's always very nice. In that case, the equation becomes just x squared over a squared minus y squared over b squared equals 1. Very simple looking equation, similar to that of an ellipse, but a minus sign makes it quite distinct. By the way, if your hyperbola goes the other way, it has a branch opening this way and a branch down at the bottom, there's a similar formula, but I won't get into that. I think it's sort of overload now. The foci, what about them? Well, as we said, they are A units from the center, C units from the center, and the vertices are A units from the center. So in this case, C is going to be bigger than A, isn't it? In general, C is bigger than A. Now, who's this B guy in the formula? We had something divided by A squared and then divided by B squared. Well, B squared satisfies the equation C squared equals A squared plus B squared. So again, the vertices are A units from the center. The foci are C units from the center further away, and B squared plus A squared equals C squared. Again, a lot of terminology, a lot of formulas, etc. Let's pin it down with a straightforward example. So here we go. Let's find the standard form of the equation of the hyperbola, say with foci minus 1 comma 2 and 5 comma 2. So it has two foci at minus 1, 2 and 5, 2, and vertices at 0, 2 and 4, 2. So we have two foci and two vertices. Notice the y coordinate here is 2 everywhere, so it's kind of going this way. So let me ask you right now, first of all, where's the center of this hyperbola? Where's the center? Well, if the vertices are 0, 2 and 4, 2, the center must be in between them, the midpoint. So it's at 2, 2. That's nice to know. The center's at 2, 2. So now we can get some information. The distance from the vertex to the center is 2 units, and the distance from the focus to the center is 3 units. So A is 2 and C is 3. That gives us a lot of information. We know what C is, we know what A is, we know the center is 2, 2. We're missing B. But that equation was C squared equals A squared plus B squared. Solve for B. B's the square root of C squared minus A squared, which is 9 minus 4. 3 squared minus 2 squared is 9 minus 4, or the square root of 5. Whew. Wow, now we know what B is, we know what A is. Here's the final equation. It's x minus h quantity squared divided by a squared minus y minus k quantity squared divided by b squared equals 1. We know all the characters. The center was at 2, 2, so h and k are 2 and 2, so it's x minus 2 quantity squared divided by a squared, that's 2 squared, minus y minus 2 squared divided by the b guy squared, so it's square root of 5 squared, also known as 5, and that equals 1. Here's a picture of that hyperbola. Interesting looking. It's got a piece going this way and a piece going this way, the two branches. I've indicated the center at 2, 2, and then you see the vertices at 4, 2 and 0, 2. They're 2 units away from the center, and then the foci are a bit further away at 5, 2 and minus 1, 2. Okay, let me go back to a minute. On ellipses, People have often asked, how do you draw an ellipse? Suppose you had a piece of paper and you wanted to draw an ellipse. Do you think of a way of drawing an ellipse? How could you perhaps do it? It's kind of a neat little trick, and I invite you to try to do this with thumbtacks. So here's what you could do. Remember, the definition of ellipse was that the sum of the distances was constant. So take a piece of string of a fixed length and attach each end to some thumbtacks. So that means that the distance between, suppose you had a pencil and you draw it taut with that string, then the sum of the distance from the pencil to one thumbtack plus from the pencil to the other thumbtack is always constant, isn't it? So you take that pencil that's next to the string and you've drawn it real taut so it's tight there, and move the pencil around and you'll preserve that sum of distance property, won't you? And you'll be able to trace out an ellipse. Kind of neat, isn't it? Try it sometime and you'll see that it really works. So you can draw an ellipse on a piece of paper. Okay, good. We went through this pretty fast, I think. Circles, parabolas, ellipses, and hyperbolas. These are big fields. There's lots of stuff here, lots of information that we haven't had a chance to touch on. For example, with hyperbolas, there's also an eccentricity. In fact, with parabolas, there's a concept of eccentricity. With hyperbolas, there are asymptotes. Remember we talked about vertical and horizontal asymptotes? Well, with these hyperbolas, there are slant asymptotes. You know, there's a whole world of ideas just waiting to be looked at if we had more time. But trust me, if you go on and take a calculus class, that part of conic sections won't be as important. The key thing here really, I think, for success in using these conic sections is, first of all, be aware of their shape, the general shape. We know what parabolas look like. We know what ellipses look like now. Hyperbolas have two pieces, etc. And also be aware of the general form of the equations. Trying to figure out what A, B, and C is kind of complicated. But if you're given an equation, can you say, oh yeah, that's an ellipse. Oh yeah, that's a parabola. That's what sort of the level that we have to sort of to rise to for success in calculus. And again, as I pointed out, the ellipses have a lot of applications with orbits of planets. The planets orbit the sun in elliptical orbits, and the sun is one focus. In fact, comets, maybe you've seen Halley's Comet or heard about it. Its orbit is also elliptical. It comes out and then it comes back and it comes back. Every so often it returns. And lots of comets have elliptical orbits, so they keep returning. And astronomers are able to calculate those orbits and tell you, hey, next week a certain comet will be visible again. There are other comets out there, unfortunately for us, that have parabolic orbits or hyperbolic orbits. So we only see them once. They come by and they go away and they don't come back again. So that's kind of sort of sad. You only see them once. Finally, let me mention that these conic sections are really complicated, so I invite you to spend a little bit of time in these two sections we just covered, these two lectures that we just covered, looking at those exercises. And the good news is the formulas are written out for us in the workbook, so you won't have to memorize them. But then you'll get comfortable with calculating A, calculating B, calculating C, seeing how the picture gets put together. And when the final picture's on the page, you'll say, okay, now I see what that ellipse looks like. I see its vertices. I can calculate its eccentricity, etc. Okay. What are we going to do next time? We're going to move on to a different topic called parametric equations. This is great stuff coming up because it uses our trigonometric skills. It uses, we'll see ellipses again, in fact. These parametric equations are very useful for describing motion, and hence they play a big role in calculus courses. The idea is as follows, very briefly. Normally, we've been thinking about functions. Y is a function of x. You plug in a value of x, out comes y. Well, now x and y will both be functions of a third variable, usually called t. And hence, x will be a function of t, and y will be a function of t. And it'll be kind of a little more complicated, but a lot more fun. So see you next time when we begin parametric equations.